Unit 7, Periodic Properties, pages 158 to 165, focusing on electron affinity, metallic character, and reactivity trends. Electron affinity is the energy required to gain an electron, which is usually a negative value. Electron affinity measures the attraction of an electron to an atom. Chlorine has the highest electron affinity. And so here you're looking at an equation where a chlorine gains an electron and then it becomes a -1 charge. So electron affinity increases as you approach chlorine, going to the right on the periodic table, and as you go up in a column. And then the electron affinity of noble gases is very small because they really don't need to attract electrons to themselves. Comparison of ionization energy and electron affinity. Note the difference between electron affinity and ionization energy. Ionization energy is the energy required to pull off an electron, which usually becomes positive. Electron affinity is the energy required to attach an electron, which is going to usually be negative. So here are examples in equation form where chlorine is changed to chlorine +1 because it loses an electron, and that would be considered ionization energy. Here the chlorine is gaining an electron and becomes negative, which is going to be representative of electron affinity. Metals, nonmetals, and metalloids. You have to review your notes from pages 15 to 16 and know these concepts. Basically, understand the locations of metals, nonmetals, and metalloids on the periodic table, as well as their general properties. Metals are usually easily oxidized, or lose electrons is oxidation. So it's because ionization energy is low. So you're going to want to relate that metals have a low ionization energy, which means they're going to tend to lose an electrons for this reason. Nonmetals are going to tend to gain electrons, not always, just usually, and so this is because the ionization energy is high and it undergoes reduction. So notice I've starred these two, and you can expect to see questions about this in your Moodle quizzes. Metallic character. As elements exhibit more pronounced properties of metals, like lower ionization energy, they are said to have more metallic character. As a result, the trend of metallic character increases as you move in the periodic table towards the element francium, which has the highest metallic character of all. Here's a graph as a visual, and notice that metallic character is going to increase going down the group towards francium and going to the left on the periodic table in a row. And remember that metallic character increases as ionization energy decreases. They have an inverse proportion. So notice ionization energy decreases going down and decreases going to the left. Chemistry of important groups on the periodic table. Alkali metals, alkaline earth metals are in groups 1 and 2. And then over here in group 7 we have halogens, and group 8 we have noble gases. Elements in the same groups of the periodic table have similar electron configurations. This is the reason why the chemistry of elements in the same group is similar. Chemistry is most affected by the electrons in the outer orbitals, and these electrons are called valence electrons. So any alkali metal is going to have an electron configuration of NS1, and you'll notice it's here in the S block, and they're all in the S1 block. And then alkaline earth metals will have NS2 all the way down the group. And then if you have group 3A over in the P block, they're going to end in NS2, NP1, and then so on for the rest of the families. And so you'll notice if the element's in the family, then they're going to have a similar electron configuration. They're going to end on the same things. As an example, you can compare oxygen to sulfur. Notice they both end on NS2, NP4. Oxygen is in period 2. So you have 2s2, 2p4, and then sulfur is in period 3, so it's 3s2, 3p4. Chemical reactivity of alkali metals. Alkali metals like to react to form +1 cations that have a filled shell or noble gas electron configuration. The reason why +1 cations are formed is because the energy required to make the +1 cation, the first ionization energy, is small for alkali metals, whereas the energy required to make a +2 cation, the second ionization energy, is very large for alkali metals. For this reason, alkali metals like to be +1 cations. Heavier alkali metals react more vigorously because the ionization energy decreases going down the column on the periodic table. Lower ionization energies make it easier to form the +1 cation. So here, as you go down the family for alkali metals, the ionization energy decreases going down the family, which means the reactivity is going to increase. It's a more violent reaction the further down in the group you go. Metals react by losing electrons, lower ionization energies, and increase reactivity. So these are some synthesis reactions with alkali metals, and where M is any alkali metal in group 1. And so if you have an alkali metal plus hydrogen gas, you're going to get a metal hydride. If you have the metal plus sulfur, then you're going to get the metal sulfide. Notice that a +1 minus 2 puts a 2 right here for the ratio. And then you could have a metal and a halogen diatomic, and notice you're going to get a metal chloride. It's a +1 minus 1 cancels ratio here. Reactions with water. If you put an alkali metal in water, you're going to always yield the same two products, a metal hydroxide and hydrogen gas. Compounds with oxygen. So we have here lithium oxide, because you're dealing with an O negative 2 versus Li plus 1, so that puts a 2 there. Then, because we have Na2O2, this 2 subscript here tells me it's sodium peroxide, which is O2 negative 2. And then we have here the KO2, and this is a potassium superoxide, and it's an O2 with a -1 charge. We know this because this is a +1, so to balance that, this must have been a -1, and that's why we don't have a 2 here. Here, that had a -2 versus +1, so that's why there is a 2 here. Because ionization, M goes to M plus, and we lose an electron, gets easier as atoms get bigger, reactivity of alkali metals increases as you go down the column in the periodic table. A hydride ion. Hydrogen has a much higher ionization energy than the rest of the alkali metals. For this reason, hydrogen does not act like a metal and lose electrons. Hydrogen makes negative ions called hydrides when it reacts with metals. And so here you would call this sodium hydride, where sodium is a +1 charge and hydride is a -1 charge. And same for lithium hydride and potassium hydride. Alkaline earth metals like to form +2 cations that have a filled shell or noble gas configuration. The reason why +2 cations are formed is because the energy required, the second ionization energy, is low. The third ionization energy is very high. So the alkaline earth elements tend to be +2 cations. Heavier alkaline earth metals react more vigorously because the ionization energy decreases down the column of the periodic table. Lower ionization energies makes it easier to form the +2 cation. So here, as you go down the family for the alkaline earth metals, the ionization energy gets lower, which means the reactivity gets higher. Here are some synthesis reactions with alkaline earth metals. If you have calcium and hydrogen gas, you're going to get calcium hydride. And remember, this is a +2 versus a -1, which is why we have a 2 right here. Calcium and sulfur are going to make calcium sulfide. +2 -2 cancel. We have calcium and chlorine gas, and that's going to be +2 -1 is going to put a 2 subscript next to chlorine. And then we have magnesium and diatomic oxygen gas, but you're going to get magnesium oxide where +2 and -1 cancel, and that's why you have one of each. Reactions with water. An alkaline earth metal and water, beryllium and magnesium, they will not react with water, but as you get magnesium reacts with steam, and that's going to give you not magnesium hydroxide as you would expect, but you're going to get magnesium oxide and hydrogen gas. And then when you have calcium in water or barium in water as a liquid, you're going to get the metal hydroxide and you're going to get the hydrogen gas, just like we did with the alkali metals. So this is really one of the only outliers, other than realizing that these two won't actually react at all. Oxygen likes to have a charge of -2 to achieve a filled shell noble gas electron configuration. So here's oxide, O -2. And then if you see O2 -2, then you have a peroxide ion. And if you have O2 with a -1, you have a superoxide ion. And halogens like to form -1 ions to achieve a filled noble gas electron configuration. So for example, sodium plus fluorine gas is going to give you sodium fluoride, but remember this is a +1 -1, and so they will balance each other or cancel. Reactivity increases going up the periodic table whenever you're talking about nonmetals that are gaining electrons. And the attraction for the electron gets stronger as the atom gets smaller. So here, nonmetals, as you go up the family, are going to increase in reactivity, which is the opposite of what alkali and alkaline earth metals would do in a family. Noble gases are unreactive because the electron configurations have filled shells. Larger noble gases like krypton and xenon form stable compounds. For example, XeF4, xenon tetrafluoride, is a stable crystal. And so you'll notice that for your noble gases, as you go down the family, you tend to start to be able to have more reactions as they get into the d orbits. Here are your two note cards for this section. First, ionization energy is the energy required to remove an electron, while electron affinity is the energy required to gain one. Metals are going to form cations because they have a low ionization energy, while nonmetals will form anions because they have high ionization energies. Metallic character is going to increase as you approach francium on the periodic table, so increasing going down the group or to the left of the periodic table. Francium has the highest metallic character, and this is a relationship between ionization energy. As your ionization energy decreases, your metallic character will increase. Oxides, peroxides, and superoxides are going to have formulas that look similar to these: metal 2 oxygen, M2O2, and MO2. This is going to be if you have a group 1 metal. Metal reactivity increases going down a group, and nonmetal reactivity increases going up the group. Here's your second note card. Alkali metals react with water to form metal hydroxides and hydrogen gas. So here would be any alkali metal in the solid phase plus liquid water yields, you'll have 2 metal hydroxides that are aqueous, and you'll make hydrogen gas. Light alkaline earth metals, beryllium and magnesium, do not react with water. So here you can see they will have no reaction. Magnesium, however, will react with steam, but it will not form a metal hydroxide. It's going to form a metal oxide plus hydrogen gas. Heavy alkaline earth metals will react with water like alkali metals do. So calcium, strontium, and barium in the solid phase will react with liquid water in order to make metal hydroxides and hydrogen gas, just like the alkali metals. Only the formula, of course, is a little different since you have a +2 - 1 ratio.